Imagine taking a piece of diamond, crushing it with pressures greater than anything found in the deepest parts of our planet, heating it beyond the surface of the sun, and watching it melt in less than a billionth of a second. Now imagine that tiny moment could help scientists unlock dramatically more energy from nuclear fusion. That's exactly why a new experiment from Lawrence Livermore National Laboratory is getting so much attention. And the most important part of this story isn't actually the diamond. It's what scientists may now be able to do with it. For years, researchers have known that diamond plays a critical role in inertial confinement fusion experiments at the National Ignition Facility. Tiny diamond capsules are used to hold a mixture of hydrogen isotopes called deuterium and tritium. Powerful lasers strike the target, creating a series of shock waves that compress the fuel to extraordinary densities and temperatures. If everything stays symmetrical long enough, the fuel can undergo fusion and release a tremendous amount of energy. But there has always been a problem hiding inside that process. Scientists didn't have a precise enough picture of exactly how diamond changes as it reaches its melting point under extreme pressure. And that uncertainty wasn't a minor detail. If the diamond changes phase unevenly during an implosion, it can create tiny pressure differences. Those differences can grow into powerful hydrodynamic instabilities, potentially destroying the carefully controlled compression needed for fusion ignition. Now, researchers have made a measurement that could finally close a major gap between theory and experiment. In laser-driven experiments at the University of Rochester's Laboratory for Laser Energetics, scientists shock-compressed tiny diamond samples and used X-ray diffraction to examine their atomic structure as the material approached melting. The entire process unfolded in roughly a billionth of a second, while the diamond experienced temperatures hotter than the surface of the Sun and pressures comparable to those found deep inside planets like Neptune and Uranus. And here's the surprising part. Scientists have been trying for about 20 years to explain why an earlier measurement of diamond's melting temperature didn't match theoretical calculations. The difference was roughly 20%, and previous models couldn't fully explain it. The new experiment produced dramatically better measurements, and the results now agree closely with simulations. That may sound like a technical physics problem, but it could have consequences far beyond a laboratory. At the National Ignition Facility, researchers are trying to squeeze fusion fuel so intensely that the fuel itself begins producing more fusion energy. NIF made history with its first fusion ignition experiment in 2022, and later experiments have continued to push the amount of fusion energy produced higher. But getting more energy isn't simply a matter of turning up the lasers. The way those laser-driven shock waves compress the fuel is absolutely critical. For a long time, researchers have used a very strong first shock to make sure the diamond capsule melts in a predictable way. The strategy helps avoid dangerous non-uniformities, but it comes with a price. A stronger first shock increases the entropy of the fuel, which can reduce the maximum compression that the fuel can achieve. And when the fuel can't be compressed as efficiently, less of it may burn before the entire system rapidly disassembles. This is where the new diamond data could change the equation. With a better understanding of when and how the diamond melts, scientists believe they may be able to reduce the speed of that initial shock. The research supports lowering it from roughly 33 or 34 kilometers per second to around 24.5 kilometers per second. That sounds like a small adjustment, but inside a fusion target operating on billionths of a second timescales, it could make a major difference. And researchers aren't treating this as just a computer simulation. They have already started designing experiments to test the idea. The National Ignition Facility has the ability to precisely tune the laser pulse, but there is a catch. A slower initial shock could require a pulse that's about 1 nanosecond longer, potentially changing the way the surrounding hohlraum and laser-produced plasma behave. Scientists still have to maintain an extraordinarily symmetrical implosion while dealing with complex laser-plasma interactions. So let's be clear about what this discovery does, and doesn't, mean. It does not mean fusion energy has suddenly tripled. The potential threefold increase is a theoretical possibility if the new approach works and other sources of performance loss can be controlled. The next step is experimental proof. But that's what makes this development so fascinating. The future of fusion may depend not only on bigger lasers or more powerful machines, but on understanding materials at the smallest possible scale. A tiny diamond capsule may look insignificant compared with the massive laser system surrounding it, yet its behavior can determine whether a fusion implosion succeeds or collapses. And now scientists have a much clearer picture of what happens when that diamond is pushed to conditions more extreme than almost anything humans can create. The next experiment could reveal whether this isn't just a better measurement of diamond physics, but the beginning of a new strategy for getting substantially more energy out of fusion. If you found this update helpful, don't forget to like the video, subscribe to Unix Media, and turn on notifications so you never miss the latest news. Thanks for watching.